Oceans, a vast deep aquatic environment home to a diversity of biomes and marine life. Still, for human interest, oceans have long been a treasured resource for transportation, food, and raw materials. But what if energy could also be directly harvested, much like green renewables, wind and solar? Ocean wave energy, harvesting power from the currents that flow through the oceans and onto our coasts. A multidisciplinary undergraduate team from the University of Massachusetts at Dartmouth seeks to contribute to this growing field of ocean wave energy with their unit nicknamed MADWEC under the guidance of Dr. Mehdi Reisi and McDonald for this year's 2022 MECC competition.
So what you see behind me is the School for Marine and Science Technology. We were able to use this to do most of our testing and work on our project. It's an off-site location that's affiliated with UMass Dartmouth. This project is also participating in the 2022 Marine Energy Collegiate Competition, referred to as MECC, which is a challenge posted by the Department of Renewable Energy of interdisciplinary teams of university students to offer unique solutions to the expanding marine energy industry that play a vital role in powering the blue economy. Well, what is the blue economy, you might ask? It's a concept that refers to the various economic assets offered by the planet's ocean and coastal resources. MADWEC unit comprises of both a power takeoff unit and charging dock to innovate wave energy conversion.
MADWEC stands for a Maximal Asymmetric Drag Wave Energy Converter. It has been a multidisciplinary venture since 2018 in which multiple senior engineering students have developed in collaboration yearly. Originally a concept, the unit reached design in 2020, where prototyping of the PTO unit was realized in 2021 and is now currently within its dry testing phase. In 2022, priority is producing small quantities of power from the PTO unit, enough to charge a battery, by mimicking ocean wave movement. In doing so, the feasibility of applying MADWEC as a self-sustaining charging unit can be measured.
The MADWEC unit is a buoy PTO ballast system designed for offshore ocean wave energy conversion. The buoy rides along the wave, creating a displacement from its original minimum orientation. This displacement is translated from vertical mechanical motion to electrical energy through the PTO unit. The ballast stabilizes the PTO while it rests until the next wave arrives, where the cycle will repeat.
The first change that we made to the system is right here. I mean, the winch used to be on flat on the ground, and it would just pull rope, and we were trying to get that to be pull off sinusoidally, but we had a lot of challenges with that, so we came up with this alternate design which puts the winch on its side, and the shaft from the winch is used to rotate this bar in a circle, which creates a linear displacement of the rope to simulate a wave. And we use the controller to change wave speed, which changes the period of the waves, and then this peg here is movable, and there's holes in the shaft, and that changes our wave height. So this system here we built, we call this the dual roller line guide. So what it does is this is going to pull in a circle, but it allows this rope here to stay linear. It's two rollers right here, so that there's no added resistance to add to the load cell data to keep that as accurate as possible. On top of this system, we have the ultrasonic sensor, which measures the displacement so that we can get that velocity data, which we'll use with the force data to calculate our power into the system. So this is our line guide system for the load cell. This keeps the load cell from sagging due to it is pretty heavy, and so just the tension in the line was not enough. So this helps to keep this really consistent. It sits on these rollers which guide effortlessly along these two rails. This attached here is the reflector for the ultrasonic sensor I talked about earlier. So this is our new split reel design. Originally, their lines were not divided. They would just wrap on top of each other on the same reel, which causes issues with binding. So what we did was create a division between the two ropes so that they only overlap on top of each other so that they cannot bind anymore. The next part of the PTO is here. This is the waterproof bearing, which allows the shaft to spin without restriction, but also keeps water out of the PTO. So here we have our outer housing, which protects the internal components from any salt water. Next, we have this inner housing, which is a 5-inch PVC pipe. We mount all our components to this, and it allows us to have easy access to any of the components when needing to change them out or troubleshoot them. Back here, we have the torsion spring. The next component we have is the slip clutch, which we replace to a more robust component. This protects us from over-torquing our gearbox. Next, there is a support bearing behind this piece of plastic. This just helps to keep the shaft aligned and moving smoothly. And after this meshing of these dog teeth gears, there's a one-way bearing in this plastic. So here we have on the output of the gearbox, we have this coupling which connects this shaft, which has the driving gear connected to it, which then meshes with the driven gears that are connected to the generator shafts. These shafts connect to the 6 generators that we have. There's 3 over here and there's 3 right here. And that's what this driving gear will make these 6 shafts spin, which in turn spins the 6 generators to create our electricity output.
Among the activities of research, building, and testing, equally important tasks of community outreach are imperative for the Blue Economy's philosophy.
Part of this project entailed outreach to the community. Our team visited Fairhaven High School and did multiple engineering accepted student stays at UMass Dartmouth. The goal of this was to allow for a better understanding of renewable energy and the blue economy. Although COVID was still a factor when doing our outreach, we were able to still conduct some surveys and obtain feedback from high school students on their interest in STEM, along with marine science and technology.
Working with a diverse, talented group of individuals is advantageous for design, efficiency, and work distribution. Managing and keeping an organized work schedule often becomes a complex byproduct to overcome.
Undertaking a large project like MADWEC involves timely purchasing of parts and diligent management of funds. Most of our parts for the PTO were purchased from off-the-shelf vendors like McMaster and Grainger. Some components like our generators, slip clutch, and gearbox were major expenses with longer lead times. So far, we've utilized 60% of our $15,000 budget for this year's build and test. In the MADWEC project, various engineering tools are utilized, from machining parts in our machine shop, using a National Instruments stack in Arduino for data acquisition, and MATLAB for post-processing and data analysis. Due to COVID-19, the team experienced supply chain issues when ordering parts as prices and lead times have drastically increased. The pandemic has also affected our ability to do community outreach in the current transitional environment for resuming normal social gatherings and events. Other challenges we face are scheduling full team meetings due to the large number of members collaborating, including 5 M&E students, 4 ECE students, and 3 faculty advisors. It has been a challenge finding a window of time that all 14 members are available to meet and discuss weekly progress, challenges, and future plans.
MADWEC is a summation of a multidisciplinary effort from its inception as a design idea to its current phase of dry testing. In the future, efforts for wet testing and AUV design are expected to further expand the blue economy and ocean wave energy harvesting.